Okay, medical applications. We've got 3 chapters left, and we've got 3 days left. That's perfect.
And 2 labs.
No, we're not going to do labs. Well, we might do 1 lab, but it's not a very long lab.
No, we're not. We're going to finish like 2 chapters and do no labs. That's about
We're going to finish all 3 chapters, and we're going to do 1 lab that's a short lab.
Sure.
It's as long as the half-life times 4 of our radioactive isotope that we're going to make.
Why don't we do that?
Tomorrow. Doesn't really matter when we do it. Maybe we'll do it today. Medical applications. There's some rather cool stuff that goes on with medicine and nuclear physics. And we learned a little bit about this when we went to the hospital. They use many different isotopes. They put many different kinds of isotopes in the body, actually, that are radioactive. And these isotopes are, yeah, they're specifically designed. So different parts of the body absorb different minerals or different molecules really well, or they get trapped in different parts of the body. Different things will go into your bone marrow, different things will go into your liver, different things will go into your kidneys. And those things are all well known. Well, if you take those things and put them in a nuclear reactor or in the presence of something radioactive, they will also become radioactive. And usually it's not, an extreme radioactivity that is going to be dangerous. Usually it's just gamma rays that are pretty low activity. Not a lot of gamma rays, but enough gamma rays you can detect them. Then if you go ahead and put those now radioactive materials inside the body and they stick in your liver or your kidney or whatever else, then you can start to map out things in the body. You can use the gamma rays coming out, where they're coming out from, how they get deflected as they go through the body, and a computer to kind of make an image of what's going on in the body. And sometimes, for example, cancerous tumors and cancerous tissue absorb certain things as well. And so you can actually put things in the body that will stick to cancer, and so you can look for things like tumors. Now, there is, damage done when there's radiation on the body, but it's different damage. The activity of the radiation matters, the intensity, which would be the intensity, how much radiation there is per second, but also the energy of the radiation. So not all radiation is created equal. Not all gamma rays are created equal. The higher frequency, lower wavelength gamma waves are more dangerous than the lower frequency, bigger wavelength gamma waves. The faster electrons are more damaging than the slower electrons. The faster neutrons are more dangerous than the slower neutrons. So essentially it has to do with how much energy, whether it's kinetic energy or just, or like frequency energy, whatever it tends to be. So the reason they call it ionizing radiation is once you get up to the point where the radiation has enough energy to ionize atoms, that's when it starts to become quite dangerous. And so ionizing radiation is considered the most dangerous kind. It starts taking apart the atoms inside your molecules in your cells, and then it starts splitting things apart and causing trouble. These are the things that can happen. Irreversible state of dormancy. So essentially it goes to sleep forever. It can commit suicide. If you damage a cell enough, it actually has a programmed response to just dismantle itself and die, so that it can be reused, so that the body can reuse its parts. But the most dangerous thing is that the cell can go into unregulated cell division, which is what is cancerous. That's what cancer is. If you cause damage to the DNA of a cell, and the cell decides to reproduce itself with that damage, it reproduces a damaged cell. And that damaged cell can sometimes be kind of go through a cascade reproduction cycle where it really accelerates it's almost like the body thinks it's some kind of new organ it needs to build or something. And so it builds a huge amount of these cells. The body does this all the time. This is not unheard of. The body is often making mistakes. and those things are called tumors. Usually, it's usually a growth of material in your body that is not in the right place, and that's usually not that big a deal. They often call them cysts or non-malignant tumors, and it's just a group of cells that are not made right, or they're the wrong material in the wrong part of the body. Sometimes people get clumps of hair or bones or teeth or whatever tissue somewhere that's not supposed to belong there, and usually that stuff can be cut out. Sometimes it's dangerous. Sometimes it can go into some kind of state of infection or some kind of state of inflammation. But usually you can just cut it out and be good to go. But cancer has a tendency to spread. When you get one of these pockets of material that's the wrong stuff, and then it goes into this cancerous malignant growth. Malignant growth means that it takes other cells and kills them to make more of itself. And that's what malignant tumor is in cancer is. So this is why cancer is so dangerous. So this is the last one that is so dangerous right here. Of course, this one here, the cell-committing suicide, programmed cell death, is also very dangerous because in high doses of radiation, your whole body can just start to die and literally just disintegrate. Okay, that's what is known as acute radiation poisoning.
Radiation poisoning.
That's right. Acute radiation poisoning will just essentially cause your body to die. It's just.
Yeah, I've seen that.
Yeah, it's not a pleasant thing for sure. The idea in the medicine field is to apply enough of this ionizing radiation in the right spot to cause that. You want these things to die, like tumors and other malignant growths in the body, other things that are bad in the body. You want them to die, but you don't want everything around them to die. And so the thing is to try to focus that radiation. Now, if that radiation is neutron radiation, you can focus it using magnetic fields, because neutrons have angular momentum, which means that they can be affected by magnetic fields. If it's a proton radiation or the helium nucleus radiation, like the alpha particle radiation, then you can guide that using electric fields and magnetic fields, because it has electric and magnetic properties. If it's electron radiation, like beta ray radiation, you can also use electric fields to guide it and even magnetic fields to guide it. You can steer those particles using electric fields and magnetic fields. Gamma rays are a different thing, because gamma rays are light rays, and you have a difficult time steering light rays. What do we use normally to steer and focus light? Mirrors and lenses. But gamma rays don't even see lenses or even mirrors. They go right through them, right? It's like they run up to the mirror and they're like, what is this? I don't know. It's just a collection of widely spaced particles, because their wavelength is so short that they just go right in between the atoms of the mirror and the atoms of the lenses and everything else. They're not deflected by it or reflected by it, except in certain cases. With high density mirrors and high density lenses, you can focus gamma rays. It's just very difficult. And so they literally use things like lead and plutonium and uranium, and they coat lenses with these things, and they coat mirrors with these things to help reflect and refract gamma rays. And they've had some success doing that. They've had even more success by coating materials made of like nanotubes, carbon nanotubes, coating those with stuff like uranium. Uranium is highly refractive and highly reflective of high frequency gamma rays. And so you can steer gamma rays and reflect them, but still it's difficult. Even in the best circumstances, it's difficult. So gamma rays cause a little bit of a challenge. Here they talk about some of the different units used to measure radiation, the amount of radiation that is being released, or the amount of radiation being absorbed, whatever you want to call it, however you want to think about it. So 1 rad, for example, is 0.01 joules per kilogram. So if you have a kilogram of person and 0.01 joules of energy of radiation hitting that person for each kilogram of that person, then that's what we call a rad. There's also the relative biological effectiveness which is also called the quality factor. And if you multiply the number of rads by the relative biological effectiveness, then you get what's called a REM. Now, the relative biological effectiveness is dependent on what kind of radiation it is. So if it's an X-ray, then it's an RBE of 1, gamma rays RBE 1, beta rays greater than 32 kiloelectron volts 1, beta rays less than 32 kiloelectron volts 1.7, and then all these other ones have slightly different RBEs, and it depends also on what part of the body. In many cases, for example, the eyes have a much higher RBE than the body, and what that does is it increases the number of REMs. If you have radiation hitting the eyes, it affects them more rapidly. It affects them more readily because the eyes have a higher RBE.
I heard REM's supposed to be low, or like gamma and X-rays, they should be like.
So when you're talking about REMs, you want to keep the REMs below a certain amount so you don't damage the body. Same with RADs. But the RBE gives you a connection between the type of body tissue and the type of radiation and how much it's going to affect the body. So different parts of the body are affected by radiation in different ways, in different amounts, you could think of it as. And there's not really a science behind this other than just measuring things and making a table like this. So the other one is called the sievert, and there's actually two more, the sievert and the gray. The gray is, they don't say what the gray is here. Oh, here it is. The gray is 1 joule per kilogram, so it's 100 rads. And then the sievert is 1 gray times the RBE, so it's the equivalent of the REMs to the rads. So there are two different versions of these things, and for the most part, you see REMs and rads being used in hospitals. In science, you often see the grays and the sieverts, but REMs and rads you'll see as well. And there are other things that are used all the time when talking about this. The Curie, for example, is at 1 decay per second. The becquerel is 1 decay per second, and the Curie is 2.7 times 10 to the minus 11. The Curie is 1 over 2.7 times 10 to the minus 11 becquerels. No, it's the other way around. There's 2.7 times 10 to the 11 Curies per becquerel. There we go. So the Curie is a much smaller unit than the becquerel. And then here we have when we're using grays or rads, that's how much you've absorbed. And then the equivalent dose is essentially what kind of damage it's going to do to the body in the sievert or the REMs. So doses less than 100 millisieverts or 10 REMs are called low dose. Moderate doses from the 0.1 to 1 sieverts or 10 to 100 REMs. And then anything greater than 1 sievert or 100 REMs is a high dose of radiation. And if you have low dosage, you can have no observable effects, slight to moderate decrease in white blood cell counts. That's one way that they can tell if you've been exposed to radiation. You can actually get temporary sterility. And then once you get to above 1, remember that 1 sievert, right? High dose right here, 1 sievert is high dose. So anything greater than 1 sievert is a significant reduction of blood cell counts. You can get nausea and vomiting, but it's not necessarily fatal. It's not necessarily a dose that's going to kill you. Then 2 to 5, nausea, vomiting, hair loss. You've seen that in probably situations where people are undergoing radiation therapy. They are often given more than 2 sieverts. They lose hair. Why would they lose hair at that point?
Because that hair is not being created.
Yeah, well, the hair is a fast-growing cell, and cancerous cells are also fast-growing cells. That's the whole reason for using radiation therapy, is to kill off fast-growing cells faster than killing off normal, slow-growing cells. So this is why fast-growing cells are more affected by radiation. It's the whole point. The eyes have fairly fast-growing cells in them as well. Many of our softer tissues have fast-growing cells, like our intestines, stomach lining, things like this have very fast-growing cells, and so those kinds of things, are killed off more readily. And this is the reason that you get things like you get nausea and vomiting. Your intestines and your stomach aren't working so well because they're not being reproduced properly when you take these higher doses. White blood cell, red blood cells are reproduced constantly in your body. So when those things start to go down, it's because of the radiation. And so this is, hair is very similar. Hair is it is reproduced very quickly, and those things are the things that are affected most readily. And you can get fatalities from 2 to 5 doses. At 4.5-ish, it can be lethal to 50% of the population within 32 days after exposure if not treated. So that's pretty intense. There are very few illnesses out there that are 50% fatal. You can count them on one hand. There's just not very many things out there that are that fatal to that many people. So right here from 5 to 20, everything gets worse, and very limited survival of that kind of with that kind of exposure. Dang it, stupid mouse is misbehaving here. Okay. Why is it doing this whole? There we go. Worst effects, and then greater than 20 is fatal within hours. Essentially, everything dies off. The central nervous system collapses, and your body just dies. So where can radiation come from? You can get a lot of radiation just from space, coming in from space. Some of it coming from the sun, some of it coming from other places, cosmic rays. There's also radiation in the soil from different amounts of radon, different amounts of radium, different amounts of uranium, different amounts of whatever in the soil that's radioactive. There's just natural things in there. And so here are some of the doses that you can get just naturally every day kind of stuff from cosmic rays. It's about 0.3 around the world. It's more as you go towards the poles, because the magnetic fields of the Earth are going in towards the poles. A lot of the cosmic radiation actually spirals in at the poles, and it doesn't hit us in between the poles very much. And that's one of the things that the magnetic field of the Earth does for us, is it shields us from cosmic radiation. Without the magnetic field of the Earth would be lifeless. So cosmic rays can create a lot of radiation. This is actually what the aurora borealis is. The aurora borealis is cosmic radiation spiraling in on the magnetic fields of the Earth, and as it spirals in and accelerates, it fluoresces. Soil and building materials, about the same as the cosmic background radiation. Radon gas can be up to, and this is in millisieverts, by the way. So this is 1 millisievert, so a hundredth of a high dose, not that big a deal. From potassium 40, where do we get potassium 40? No, eating bananas. Potassium 40 is just a naturally occurring isotope of potassium that is radioactive, and we eat it when we eat bananas and other things. Carbon 14 we get from eating just about anything we eat, and 226 radium we get. That's just in the soil and other places. So, and radium decays to become radon. So, then medical and dental stuff, up to, and these numbers are kind of high now. They're actually less nowadays because they use digital X-rays. They can expose us to fewer X-rays for fewer amount of time to get the same image, get the same quality image, or even better quality image. So we're talking about a couple of millisieverts per year of radiation exposure. Not that big a deal. If you spend a lot of time up near the poles, South Pole, North Pole, you're going to get more. And sometimes they even wear badges, radiation badges, just to make sure they're not spending too much time outside getting radiated. And many of their habitats down there are actually specifically shielded for that. You don't necessarily need a lot of shielding. Just a metal roof is usually enough to shield you from radiation on the poles. But sometimes you need to take a little more precaution, have a little thicker roof, or maybe put a little lead up there. So, in hospitals they have, all kinds of ideas of how much we talked about that at the hospital. Let's go learn about something else here. So, using radiation in medicine has been used for a long time. Using radiation to kill off tumors has been used for a long time. In fact, I think it was Röntgen who was the first one who did it. The guy who invented X-ray, or not invented, but discovered X-rays, actually started using them to do things. He started realizing that this ray had special properties, high energy properties. If you expose yourself to too much of it, you got a little bit of damage. So he said, might be able to burn off some of these, skin tumors from skin cancer. And he started using it in that way. And so it's been a long time, and nowadays it's used for a lot more things. This right here is commonly called the gamma knife, and it's, they actually did show us something similar to this in the hospital, although not exactly like this. I like to see the real version of it, so let's go look at the real version of it. The gamma knife is usually used on the head, for one thing. So this is what it usually looks like, and this is what the one that they were showing you, essentially, where you have this big thing that you can put people into, but it's usually their head. And this is what it looks like if you tear away all the outside coverings of the gamma knife. These little discs here are pieces of radioactive material, usually cobalt-60, I think, or is that what they said, cobalt-60? Yeah. But what they do is they clamp your head into this system here, and they put you into this. They put your head into this thing, and they can adjust this. They can remove some of these and insert other ones and put in stronger ones in some places. But the whole idea here is that you get gamma radiation coming off of these, so really strong X-rays. And remember, gamma rays are light rays. So you can actually get them to cancel out so that you get light and dark spots like we saw with the diffraction patterns. But you can also make it concentrate all at one point with a really bright spot and have all the other spots inside the head be dark spots. In other words, you can get all the gamma rays to go to one point and have almost no gamma rays anywhere else. And the advantage of that is that you can have a really strong ionizing radiation right at the site of your tumor. And you can kill the tumor without ever cutting open the head. Before the initiation of the gamma knife in the medical field, people were just turned into chopped suey on the medical table. I mean, if you cut into the brain, you are going to ruin somebody's life, almost inevitably. You cannot cut into the brain and not have adverse things. And usually, I mean, so many times you go in to one of these surgeries as a patient not knowing if you would come out conscious, not knowing if you would come out a human being. Your brain might completely toast when they were done. And so you were just a vegetable and just, there was nothing to do except let you die. And so this really has changed a lot of things. As you focus in these gamma rays at a single point, you get very low radiation or no radiation. Some of the radiation actually cancels it out because you have the peaks and troughs lined up. Some radiation is just lower radiation because it's not focused, and so it's not a big deal for the rest of your brain, not as big a deal, I guess. And then you have this tumor right here that just gets killed off. And you can go through several sessions of that. And that's the idea of the gamma knife. It is a rather intense process. You have to get your head all clamped up into this thing, and doesn't look like a very fun process, of course. And you usually have to sit there for quite a while and not move or anything. Another really interesting therapy that they use with radiation is in Fermilabs, they have an accelerator. Fermilabs is in Chicago. It's a great big scientific laboratory up there, run by the Department of Defense, and they have a huge accelerator ring out there, kind of like the one in Europe. This is actually the miniature one of the one in Europe. They thought this one would be big enough to do what they wanted to do, but it wasn't, so they built the big one in Europe, which is like 10 times bigger. But this is still pretty big. It's like 12 miles around or something like that. And the idea of this is you get these particles going around and around and around and around, faster and faster and faster, and then you collide them into each other. You get particles going in both directions, and you run them into each other and break them all apart, and you look and see what you get, right? It's the age-old thing of what's inside of that toaster. I'll break it and find out, right? This is breaking open toasters with atoms. But you get some really unique radiation here, really unique high energy radiation that you can't get anywhere else in the world. And this tunnel is underground. What you're seeing here is just a road that's on top of the tunnel. This tunnel is several stories underground, and it's helium cooled, magnetic electromagnets, and all these crazy technology going on. So they actually have a place where they take a beam out of that loop. And it can be a beam of different things. A beam of high energy neutrons. It can be a beam of positrons. They have different beams that come out. But they have this place where this beam comes out where they can put a patient in here, and you can actually see a little target on this person here. They're using these red lasers to target where they're going to hit this patient with this beam, and they have these different beams here. And usually they have to put this person in some kind of a restraint so that they can hit them just right and not hit them incorrectly. Sometimes there's actually a chair that they lower them, and this chair is on an elevator that goes down. Like you put them in the chair and you strap them all in, and then they go down this shaft, like 3 stories, and they're all by themselves down there during the process. And there's also one that they can lay down a patient in. Here's one where they've strapped the patient down with this netting. That just looks really uncomfortable.
What would you do to fix the cancer?
So I've actually been there, and I've actually seen that chair up at the level where they actually weren't running the beam when I was there. That was down for maintenance. It only goes down for maintenance every few years, and just happened to be one of the years that I was there. But it's a really interesting use of radiation and a way of getting a very unique treatment. Of course, only one person can be lowered into it at a time, and there's only one of them in the United States. That's it. So that is another unique and interesting use of ionizing radiation in and then you have proton therapy, which is the same thing, which is acceleration of protons. Protons are much easier to accelerate than neutrons because they're charged. So you can use an electric field to accelerate protons. So proton therapy machines, they actually have one of those here at the hospital, I believe. I don't know if they showed us that. I don't think they showed us that room at all. But actually, I think they may have showed us one of them. They have a small one there. But they also have positron therapy. So a positron is a particle created in a nuclear process. It gets shot out of the nucleus, and it's essentially an electron that's positively charged. It has essentially the same mass as an electron, same charge except positive. So it's the electron's sister antiparticle. It's an antimatter particle, and those positrons can be used to do things. So here's a positron emission tomography machine where they use those positrons to map out things, to actually look for things. And then there are positron treatment therapy machines as well, where they actually bombard the body with positrons, another high form of ionizing radiation, to kill off things. So anyway, lots of interesting things. Food is also irradiated. We use gamma radiation to kill off things in food, to kill off bacteria and things on the food. And usually they just bring it close to a material like cobalt or cesium, and those are enough. Those give off enough X-rays and gamma rays at low enough. It's high enough energies that it kills off bacteria and things, but it's low enough that it doesn't damage the actual vegetables or the actual food. So they do this with vegetables. They do it with eggs. They do it with all kinds of things that have stuff on the outside that might be dirty. And so usually it's kind of like this, where it's built right into this. It's built right into the factory, where the food goes around on a conveyor system, and as it goes around on the conveyor system, all sides of it are exposed to this material, and it can be stored when it's not being used in a pool underneath. Water is really good at blocking most forms of dangerous radiation, particular neutron radiation. So it's good to store things in water. The one problem with this is that it can actually break down. This radiation can also break down some of the important nutrients that we need, including some of the bacteria that we need in our bodies. So that is one problem with it. You make your food last longer, and you also kill off some dangerous bacteria, but you also kill off some good bacteria, and break apart things like you can sometimes break apart vitamins and things like this that are quite important for the body. So that can be a bad effect. Okay, so let's talk about fusion, fission, and nuclear weapons. We've talked about nuclear weapons a little bit. We haven't talked about fusion so much. What is fusion? Fusion is quite simply the creation of a more stable atom from a less stable atom. There are some atoms that are very stable and some that are not so stable, right? What?
Radium naturally.
Okay, so that's actually called transmutation, where radium radiates and then becomes a different thing. And that natural transmutation is usually happens when something in the nucleus changes. It goes through a decay, a radiative decay, and it throws out a particle, and then so you have a proton that becomes a neutron that becomes a proton, rather. And you get radium to radon. So this is a little bit different. Fusion, you essentially take two atoms and bring them together to make a new one that is more stable. So in fusion, you start with two and you end with one. In natural what did I just call it? Transmutation. There you go. Natural transmutation, you start with one, you end with one. And then in fission, you start with one and you end with two. So if you break it apart, it's fission. If you put two together to make one, it's fusion. And if you have one and it changes to something else, it's transmutation. So fusion is the bringing together of two to create one. And you might have some radiation particles coming out. You definitely will. But there'll just be one atom in the end. And the most common type of fusion in the universe is the fusion of hydrogen to helium. Hydrogen is a very unstable atom. It easily combusts with oxygen, for example. It easily combines with other things to make molecules and to undergo chemical processes. It's just a very energetic atom that is quite unstable. Helium, however, helium-4 in particular, is very stable. There's two protons and two neutrons. Those neutrons create a stabilizing influence with all that cosmic glue they put in there, And so this is what goes on when you have two hydrogen atoms close together with sufficient energy nearby. They will combine to make hydrogen 2, which essentially means that one of these hydrogens, which these are just protons, right? One of these hydrogens actually decayed into a neutron. And so this becomes a proton and a neutron. So you have two hydrogens, two protons essentially, that become one proton and one neutron. And in the process, what happens is that you release a positron and a neutrino. So you release a positron and a neutrino, and this is the energy that's released in that. This is the amount of energy that was liberated, you could think of, from the hydrogen atoms when they were by themselves. So it's less energetic to be deuterium. This is called deuterium. It's less energetic to be deuterium than it is to be two hydrogens. So it wants to become that. It wants to become deuterium because it's less energetic. Then that deuterium can combine with another hydrogen to become helium-3, which is called tritium. Tritium has got one proton and two protons and one. Sorry, this is not tritium. See, is tritium helium-3 or hydrogen-3? Tritium is hydrogen, actually, I believe. Tritium is hydrogen-3. It's one proton, two neutrons. So this is just helium-3. Helium-3 is considered, I don't remember what it's called, but anyway, helium-3 is considered an unstable isotope of helium, but not terribly unstable. It's not necessarily radioactive, for example. It's just not terribly stable. So you have one proton and one neutron combined to give you two protons and one neutron. And this releases some energy in the form of a gamma ray, and it gives off 5.4 mega electron volts in that gamma ray. So that created even more energy. So this one was an even more unstable thing, released even more energy when it became something even more stable. Then if you have two helium-3s hanging around, they will combine to make one helium-4. So in these helium-3s, you have two protons each and one neutron each. Each of those neutrons comes together into the helium-4, and one of the protons each comes into this helium-4, which is extremely stable. And then you end up with two protons left, or two hydrogen and one atoms left. And that releases 12.86 mega electrons volts. So the whole process releases 26.7 mega electron volts of energy just for two hydrogens. Actually, it ends up being four hydrogens total, becoming one helium, 4, 2 neutrinos, and 6 gamma rays in the end. So that is hydrogen fusion, and that is the main process that's going on inside of stars. That main process and this energy that's being released every time one of these happens, this amount of energy is released, and over the gazillions of these things that are in a star, that's what makes it hot, that's what makes it glow, that's what makes other things, inside of stars, other kinds of atoms are being created, like iron and carbon and nickel and whatever. All these heavier elements above hydrogen, helium, lithium are all being created inside that star. In fact, even lithium and helium are being created in that star. So hydrogen is by far the most plentiful thing in the universe. 99% of the universe is hydrogen. But inside of stars, that hydrogen is becoming helium, that helium is becoming lithium, that lithium is becoming beryllium, and so on and so forth. It's just building more and more atoms using fusion. So all those atoms in the periodic table, built by fusion, the first one in this process that we just showed you, helium. And that's what they're studying in lots of different places. In this right here is a pool of water. This thing is much bigger than it looks. It's like probably, if you take this building and made it into one single square, actually just take the other building. The other building, it's about the size of this thing, this pool. And it's a big pool of water with these detectors at the bottom, and it's at Fermi Labs again. And these things are detecting neutrinos. These are photomultiplier tubes. The neutrino comes in and it hits a material inside of that tube, and that material fluoresces, that material glows, and that glowing is multiplied inside the tube, and so you can detect the neutrinos that way. And that's one of the things that they use this material for. We talked about before this this stuff here, the stuff that glows, right? This, that's one of the things they use for that for. There's lots of other materials they use as well. There's a nice little supernova 1987A. Heavy elements being created in supernovas and being thrown out in the universe by the explosion of the star. So here's another fusion reaction. Hydrogen-2 becoming helium-3, hydrogen-2 becoming helium-3 and a neutron, hydrogen-2 and helium-3 becoming helium-4, hydrogen-2 becoming helium-4, lots of different things that you can do here. Now, you can create a process of this. If you have a high enough density of this, you can create a self-sustaining process like a star. You can create a little star on your own. The problem is that getting these things to all combine and to stay in one place, because, you know, it's hydrogen. Hydrogen is protons. They don't want to get close to each other. You really have to force them to get close to each other. At the center of a star, gravity is what does that. Gravity, the gravity of all the mass in the star holds those hydrogens close together. But it's very difficult to use gravity anywhere else because we don't have that much stuff to make that much gravity. And so what we use is we use magnetic fields to manipulate these things. Also, the magnetic fields are used to contain the neutrons, because you'll notice that neutrons are often popping out in these reactions, and neutrons are extremely damaging. They're very heavy particles of high energy, and so they're very damaging to this thing. So what we do is we use this thing that we call a tokamak. So the big one that was being built in Europe was called the International Tokamak something radiation. I don't know what it stands for, but it's this huge thing, huge project. The tokamak is a tokamak is like a donut-shaped thing, a donut-shaped fusion reactor where the magnetic field is created by these electromagnets going this way and going this way and going out around this way. So all these different electromagnets in different orientations to contain these particles and to accelerate them around and around and get them into a really, really high density, high energy state. And then if you can ignite that state into a fusion reaction, then you can create a ton of heat, and then you can use water or whatever to carry that heat away into a generator. You know, you can use it to make steam, turn generators to make electricity. The beauty of this is that it uses hydrogen. And we have more hydrogen on this earth than you can count. I mean, there's just so much hydrogen on this earth. All the water on this is made of hydrogen. Just about half the stuff in the soil is made of hydrogen. There's all kinds of hydrogen on this earth. Hydrogen's everywhere. And so it's like free energy. And it doesn't really make any waste products either. The only real waste product is that the reactor will eventually get destroyed by the neutron radiation, the neutrons bombarding it. It will be somewhat radioactive. So after maybe 50 years, you might have to discard your reactor and rebuild it, and that would be your only waste product, really. Nothing else. There's no radioactive control rods. There's no radioactive fuel rods. There's no coal. There's no coal dust coming out one end of the coal slag or whatever they call that stuff, all that junk. There's no contaminants in the atmosphere. There's nothing else. It's just very simple. We've been able to make this work, but we haven't been able to make it work cheap enough to make electricity from it that is affordable. So that's a matter of time, I think. But here's a picture of the inside of the ITER tokamak. They've got all these surfaces that are I think mostly made of uranium. Actually, they're highly polished uranium, and the highly polished is so that they refract all the radiation, and after time they get kind of damaged. These are all pictures of the shiny ones, and you can see they wear clean suits when they go inside of this, and they have robots even that go inside of this to clean it and polish it and everything else to make sure that it's in good shape. But after a while, this is what it looks like, and this is why all those pieces in there are replaced. This is why they'll have all these separate pieces in there so they can be replaced. You can take them out and replace them. This is from essentially damage from particles, radiation particles and hydrogen particles that have escaped their containment, escaped their magnetic containment. They hammer into the wall and they melt the walls, and then you have to replace those plates, and you get, and then you can start over again. They actually have images of the inside of it while it's running. That's not actually that one. Here's a nice picture of a cutaway view of what it looks like when it's running, when it's not running. Inside of there. So it's kind of cool. Here's another version of it. They have many different versions of containing this using magnetic fields. Sometimes it's just a very donut shaped, and sometimes it's got this vortex going on inside of it. And that's a new version of this idea, where instead of just going around and around, it actually goes around and twists it, and they're actually able to contain it better that way, and also get it to a higher density. So there's many versions of this tokamak around. So this is another version of this tokamak where they're using magnets to contain this stuff. And they do this all over the world. They're doing this at just about every university has their own version of containing this plasma. The university I went to did. They're always trying to make a better containment field, a better way to create this fusion. And they're also studying that at the laser in California. At the NIF laser, they also study fusion, but they study fusion by putting their hydrogen inside that little gold ball and then zapping with lasers on all sides and compressing it down so that it's as dense as a star. So they're actually trying to create a star, but they're still studying the fusion processes so that they can use that to make energy. So it's not really that much different. Then of course you have to have a superhero or supervillain. All right. Now fission is, like I said, the exact opposite. And we learned a little bit about this in our video, where they tried to make uranium into something bigger. And what they found is that they shot a neutron at uranium. It didn't absorb the neutron. The neutron actually split the uranium atom into two things. And one of the things that uranium can split into is strontium and xenon. Strontium-95, xenon-140. And in the process, you get out 3 neutrons. Now, this is not the only thing that can happen. There are lots of different fission reactions that can happen. And remember, we call this the parent and these the daughters, right? So you have a fission reaction. You get strontium and xenon out plus 3 neutrons, and these 3 neutrons come out with a lot of energy because there is a mass defect here. The mass of uranium, if you actually weighed the uranium before and then weighed all these products after, the weight of these ones afterwards is less. There's missing mass, and that mass is tied up in the uranium. It's tied up in the bonding of the nucleus and the neutron interaction. Here, it takes less energy and less neutrons to bind these 2 atoms. And so there is much less energy. It gets released in the form of 3 neutrons at high speed. That kinetic energy of those neutrons, is equal to the mass defect times the speed of light squared. So mc squared for the energy. And so they want us to calculate the energy released. By doing this, we calculate the energy released by using the atomic masses of these molecules here and the mass of the neutrons. Take the mass of this and subtract off the total mass here, and you're going to get a mass defect of 1.008665. No, sorry, that's the mass of the neutron. So here are the masses of uranium-238 is 238.05. The mass of strontium-95 is 94.919. The mass of xenon-140 is 139.92. And the mass of each neutron is 1.008665, so you multiply that one by 3. Then you take the mass of the products, add them together, take the mass of the original, and subtract the mass of the products, and you get 0.183791 atomic mass units. So essentially a 0.818 of a proton's mass missing. That's the missing mass going from this side of the equation to this side of the equation. We plug that into Einstein's equation, E equals mc squared. We get 171.2 mega electron volts of energy released for every fission of a uranium-238 into strontium-95 and xenon-140. Every time one of these happens, you get It's 171.2 mega electron volt. That's a lot of energy per atom. And considering how many atoms you can have, I mean, how many atoms you have in a piece of uranium this big is just uncountable. I mean, it really just is. It's, something times 10 to the something huge, 10 to the 30 or something. Maybe not quite that many, but it's a lot. Okay? It's a lot of atoms. At least 10 to the 23. So we call this kind of fission is actually spontaneous. It doesn't require anything to happen. When you dig up uranium-238, this is happening. And this is why uranium-238 is actually warm. Uranium-238, when you dig it out of the ground, is warm metal. It's warm to the touch. And this is why it's warm, because of that energy being released and that mass effect of the spontaneous radiation, the spontaneous fission, actually, that's always going on. But the neutrons coming out in this reaction are not energetic enough to cause more radiation, to cause a chain reaction, essentially. It's not in, those neutrons can't go and hit another uranium-238 and cause this to happen. This just happens because uranium-238 is unstable and it happens spontaneously. It happens at a particular rate, about this many times every whatever amount of time. And it's fairly slow. The half-life of uranium-238 is like, I don't remember, 8,000 years or something like that. It's a long time. So the half-life of this is not something that's going to happen overnight and all your uranium is going to be gone and be turned into strontium and xenon. It's just not going to be that way. However, there are types of uranium that can easily be induced into a fission reaction by these neutrons. Uranium-238 not, but these free neutrons can hit a uranium-235 atom and cause uranium-induced fission. So if one of those neutrons comes out of uranium-238 and hits a uranium-235, that one will split into barium and krypton. Uranium-235 will just split with that when that neutron comes in, just like that. The problem is there's just not that many uranium-235 atoms in natural uranium. They're very few and far between. So it's very rare when one of these things gets hit and it actually goes through this reaction. However, notice that 3 neutrons come out of this reaction as well, and they're high energy neutrons also. So if you can get enough of uranium-235 all in one place, then for every neutron you put in, you're going to get 3 out. So every neutron comes into a uranium-235, you're going to get 3 going and starting 3 more reactions. And those 3 will all start 3 more. So the next one will be what? You have 3 starting, and then 9, and then 27, and so on and so forth, right? And so you get this, that's where the chain reaction starts. And it's quite a chain reaction. So uranium-235 is not only warm, but if you have enough of it in one place at a high enough density, it will just explode. It will spontaneously explode into a reaction that is so energetic that it creates a nuclear bomb.
Transmutation is one chain, another fusion is one.
Is 2.
Is 2 going to 1.
And fission.
Is 1 going to 2.
That's correct. So uranium-235 will support a chain reaction because of the neutron in, 3 neutrons out thing, right? Uranium-238 will not go through that. If you shoot an atom at uranium-238, it doesn't go through fusion. It won't go into a fusion process. It will actually turn into plutonium. It will go into neptunium. If you shoot a neutron at 238, a high energy neutron at 238, it actually becomes neptunium. It goes through transmutation. It goes through man-induced transmutation, and then it becomes plutonium 238. It becomes neptunium 239, and then plutonium 239. There we go. Is what happens if you shoot a neutron at 238. But 235 splits if you throw a neutron at it. So, of course, you can use this. You put that nuclear reactor inside of a system that takes the heat away and then turns that heat into steam, and then you can turn a turbine, right? And that's how you do it. You usually have 2 water systems. One water system that takes the heat from the reactor and heats another water system that puts the water to the turbine. You don't want this water going directly to there. Why not?
It's irradiated.
Yeah, it's heavily irradiated. In fact, all these pipes are going to be lead lined so that the radiation doesn't escape the water when you go from one water system to the other. So they're going to be all lead lined to prevent the transfer of radiation. And all of this is going to be completely covered with lead and concrete and steel to keep in the radiation. This entire thing will be underwater to prevent neutrons from going out. And then keeping it underwater also just kind of keeps it safe. And then you put these rods really close together. These fuel rods are the ones that have your uranium or your plutonium in them. And then you put control rods in between that absorb neutrons. And if you absorb neutrons, you slow down the reaction. Right? If you absorb them all, you stop the reaction. You can't absorb them all, but you can absorb a lot of them. So as you put these control rods deeper into the reactor or further out of the reactor, you can slow it down by putting them in, speed it up by pulling them out. And that's how you essentially adjust the temperature of your reactor. As your fuel is getting older and older and older, you generally have to pull those rods out further and further and further. When your fuel is brand new, you just shove them in because you don't need, this thing is easily hot enough to melt through the concrete, to melt through all the steel, to melt through the crust of the earth. Okay? If this thing goes into high energy reaction, it literally will get hot enough to melt through its surroundings, to melt down into the earth. That's how hot it can get, and that's what they call a meltdown. And if it melts down through its reactor core and through the building, it will essentially melt into a puddle of uranium. And then it will separate. It will separate into 238, 235, and then if you get a puddle of 235 in there, it can blow up, right? And that's where it becomes dangerous in a meltdown. A partial meltdown means that it never gets to that point where it actually combusts, or not combusts, but fuses, goes into a fission reaction, but chain reaction. A partial meltdown means that it melted, but it didn't go through fission chain reaction. And then a full meltdown means it melted all the way down and then actually went through a fission chain reaction, turned into a little bomb. Sorry, what was your question, Scott, or comment?
Whenever they do that, right, they have carbon in between them?
Yeah, so these fuel rods are made of materials that absorb neutrons, and graphite is something that they have used for those. There are other materials that they've developed over the years that are better. And usually the whole thing is in a pool of water. And water is a good neutron absorber. So that's another safety thing to have. If it's not in a pool of water, then they have it in a pool that they can fill with water in an emergency.
So graphite can take all the heat?
Graphite can take the heat as long as you keep the heat controlled. Graphite will melt in there as well if it gets hot enough. I mean, if you get a runaway reaction in the reactor, it'll melt everything around it.
Do you have anything on this earth
I don't know that there's anything that we know of that will withstand that kind of heat. Just about anything, it will just break down everything and turn it into its element, whatever it is. And most of those elements are metals, so most of them melt, right? And even the ones that aren't metals can melt, really. They just have really high melting points. Things like silicon and carbon, they have melting points. They're just really high. But nuclear reactions put a lot of heat into the environment. So the biggest waste product of nuclear reactors is the heat, actually. If you're upriver on the Missouri River from the plant in Brownville, it's 2 degrees cooler than it is downriver in the river, and that's a big river. But that's a significant change in the water temperature. And downriver from that, it's actually affected the ecosystem. Certain fish do not thrive downriver as they do upriver. So upriver from there you can catch certain fish. Downriver you can't catch those fish. It's very rare to catch those fish because the fish don't like the warmer water. They've migrated upstream. It's really interesting, and that power plant brings a lot of water through it. It pulls it through a lot of water, so it's pretty impressive. And again, you can calculate the energy that comes out of this by calculating the mass defect. The mass of the parent is more than the mass of the daughters, right? And the difference in those masses, plug it into E equals mc squared, and you will get the amount of energy released in the reaction. All right, let's see.
You still call it parents and daughter when you have fusion?
I can't remember, probably.
Okay.
When you have just enough matter or matter density to undergo fission, they call that a critical mass, in case you're wondering. It can either be just enough matter in one place, or a high enough density of matter. So the simplest bomb that we talked about, which is which was Little Boy during World War II, just has the two pieces of uranium-235, and they propel one towards the other, and they create an explosion after making this critical mass. And this was technically a supercritical mass. So a critical mass means that you just have enough. Supercritical mass means that you have more than enough. And they definitely over-engineered this. In the implosion type bomb, they have the surrounding explosives, and they actually show it pretty well here, because there are different layers of explosives. The outside explosives are, let's see, I believe that those are slow explosives, and they're shaped specifically to explode inward. And then these inner ones, these gray ones, are actually fast explosives. And they're not even showing that correctly, because they're showing, that's correct. So they call them high explosive lenses, but what they really are is you have a slow explosive that ignites a fast explosive. So the slow explosive is designed to ignite that fast explosive from the outsides inward, so that the outside of the explosive is exploding before the inside of the explosive. And then in the end, what you want is all these explosives to hit the center at the same time. And then they compress the plutonium piece in the middle. So this plutonium is a subcritical mass of plutonium, but when you compress it, it makes it a high density supercritical mass. And then it creates the explosion. And then you have thermonuclear bombs, where in a thermonuclear bombs, which is often called a fusion bomb or an H bomb, you use one of these bombs as the trigger. You use one of these as the fuse. And so you have and this is oversimplified. It's not nearly as simple as this, and the shape is not nearly as symmetrical as this actually. But you have this is your plutonium with your shaped charges on the outside. So you create your nuclear bomb here, and but on the outside of this, there's on this one side over here, there's a neutron reflector, and actually there's two reflectors. There's this neutron one, and then there's this beryllium one, and then there's this uranium-238 one here. And so this uranium-238 is a highly useful material, because it both reflects materials, and it's also going to create fast fission, a really quick fission reaction, which happens on the nanosecond scale. And then you have all this styrofoam in here. And it doesn't really have to be styrofoam. It can be pretty much any kind of plastic material. It needs to be some kind of organic material that's a polymer material. And it absorbs all kinds of gamma radiation, prevents the gamma radiation from escaping. So it absorbs gamma radiation, and then it flashes into more energy there. So it creates a flash energy in there. And then down in here we have more plutonium and uranium, and then we have what's called lithium deuteride, which is essentially deuterium, it's hydrogen. And that's why it's called a hydrogen bomb. So this lithium deuteride has lithium and deuterium in it, and the deuterium goes into a fusion reaction to create helium. So you create a little star here, which this releases a bunch of energy like a normal nuclear bomb would. But this one here will multiply that original bomb by 10 or 100, or even more. This part of the package and all these other components are important. Now, it's kind of macabre to think of, bombs and weapons as part of science, but it actually is very interesting, and it's led to a lot of innovations. Survival is one of the motivating factors for invention, and certainly weapons are part of survival. So when they were first building this bomb, they were just dropping them out of airplanes, but then it wasn't very long before they started putting them on missiles. But the problem is that they wanted to put this missile so high in space that they could literally just drop them from space. Because dropping them from space means that you cannot intercept them. When you drop something from space, it's going so fast by the time it comes below, 50,000 feet. Below 50,000 feet is where missiles can get to usually. But by the time it's hitting 50,000 feet, it's going so fast if it's dropped from space at 200, 300, 400,000 feet that there's no way you can hit it with anything. By the time the missile sees where it is and so it can lock onto it, it's already passed the missile. So missiles just cannot hit these things. Well, back when they were first building them, they couldn't. Now they can. But anyway, the point is that missiles and any other kind of munition, these would be impossible to stop if they were dropped from space. But the problem with dropping something from space is that it gets super hot when it re-enters the atmosphere, and it melts. It turns into a little meteor. And then the bomb is destroyed in space. It doesn't even go off. It just gets melted down and destroyed, and all this, radioactive components just get spread throughout the atmosphere. Just catastrophe. So they said, well, actually, we need this plutonium on the outside anyway. This is a necessary part of the bomb. Why don't we just make it thicker and let it melt in the atmosphere? And so when you look at a ICBM, which is Intercontinental Ballistic Missile, on the top of an ICBM, you see these things here. At the top of an ICBM, we have all these little cones up here. And those cones are literally, each one of those is one of these H-bombs. And you can see them here. And here they're not even painted in any particular color. That's actually the uranium-238 right there. And inside of this, and this thing is hollowed out on the inside, and on the inside there is a nuclear bomb in the inside cavity. In the nose cone of these things, there's a little bit of telemetry stuff going on. They've got some radar and other things, and they've got some steering fins on the back that they can steer it with a little bit so that they can guide it exactly where they want it to go. But it doesn't even take much of that. I mean, those things are minor. The inside, the most of it is just pure nuclear nuclear bomb. They call it the MIRV. It's the something reentry vehicle. What does MIRV stand for? Multiple independent. There we go. Multiple independent reentry vehicles. So they're called the MIRVs, and you can put several of them. Each one of these being like 100, kilotons or three. Most of them are actually dial weapons. You can actually choose how big it's going to be. So you just essentially enter a computer command in, and it decides how big it's going to be. And how it decides is it going back to our going back to this. It decides essentially by injecting certain amounts of tritium into the reaction. If you inject tritium in while this is going on, it increases the reaction even more. And so tritium just being another component of hydrogen. So if you inject a little more hydrogen in there, it increases it into an even bigger hydrogen bomb. And if you inject less of it, it's smaller. More of it, it's bigger. So
you need a nuclear bomb and other stuff to make
Right. Nuclear bomb is the trigger for a hydrogen bomb. The nuclear bomb still provides a lot of the explosive energy. It's still, it's still a part of the energy, but it's only a fraction of it. This is the big daddy when you're done. So a conventional chemical bomb, you have 90% blast energy, which is pressure wave, 10% thermal. For a conventional nuclear bomb, the energy profile is 35% thermal, 50% blast. Radiation that comes out immediately, like before anything. The first thing that comes out of a nuclear bomb is radiation. And that radiation, the first radiation, the prompt radiation is 5%. And that's almost all gamma rays, and it's so powerful, so energetic, that right next to the nuclear bomb, things are just literally disintegrated. They're turned into just pure protons. It just takes apart the atoms, really close to the nuclear bomb. Then you have 35% thermal, and then delayed radiation are pieces of the bomb that are radioactive. Literally pieces of the plutonium or pieces of the uranium that didn't undergo fission or fusion. Those things fly outward and get stuck to things. And that's what we call fallout. So delayed radiation is the fallout, and that stuff is actually easy to track down. They have teams that go out and actually collect it. It sticks itself to other things, but they just collect pieces of anything that has, it's easy to find because it's radioactive. So you just go out and find things that are radioactive, put them in your truck, and take them back to the lab. And so you can pick up fallout pretty easy. The only part of fallout that's not easy to collect is when it sticks to dust in the air. If it sticks to dust in the air, which it often does, and dust on the ground that goes into the air, and then gets blown all over the place, that's hard to collect. That's a small percentage, but it's still significant. And then if you have radiation-enhanced nuclear bomb or a neutron bomb or a hydrogen bomb, then so each one of these is less blast, you see. So 40% blast, prompt radiation 30%. So that's hugely damaging, right? Thermal 25%, delayed radiation 5%. So this one's pretty clean as far as fallout goes. Much more than this one. This one, a lot of blast. But of course, to make a conventional chemical bomb the size of a nuclear bomb, you literally need tons of chemical explosive. You can't carry that in a plane. You have one bomb, a plane can carry tons, but it could carry one bomb that was the size of a small nuclear bomb. The biggest plane that we've got. What's that? No, the biggest conventional bomb actually was dropped by President Trump for the first time. President Trump dropped the biggest ever conventional bomb that was like the size of a small tank. So it was several tons of chemical explosive, and it was something like 1/4 the size of Hiroshima's bomb or something like that, or 1/10 the size of that.
Where did you drop that at?
Syria. That's the one he dropped on the airfield that was distributing chemical weapons, and he just decimated an entire military base. He destroyed. This military base was like a couple square miles. He destroyed it. That's a huge bomb. Not many bombs can go beyond a few hundred yards. Most bombs destroy things like the size of a football field. That's a big bomb. To destroy something like a square mile, whew, that's incredible. You have a blast radius that big. That's
Down there, or out overseas, we call in one of the C-130 gunships, and it's shooting 150 millimeters, it's an Abrams tank can outside, and 2 mini guns, and you call it in for overwatch for us for like an hour, and that thing was set up every hand.
Yep.
So there.
Yeah, chopped salad. It's one way to do your landscaping. And then tomorrow we'll do chapter 33, particle physics. This right here is what we call the Alice detector, I believe. And you can see for size, there's a person right there. This is the beam for the Large Hadron Collider. The beam right there is something like 6 feet. That's about a 6 feet across beam right there, and that's where the actual particles go through. They are usually accelerating lead nuclei, so lead ions are going through here. That's the particle that they're firing through them and running into each other. But you can see all these layers in here. Each one of these layers, you can kind of see some of the scintillating materials in here, some of these glowing colored things. But all these things detect different things out here. Even these pipes are filled with things that detect things. All this stuff down here, they're all detectors. And in the end, you see something. Like this. So this is actual data that comes out of it. Each one of these dots represents a detection. And you can look at it from different angles, and you can look at different detectors. There are different detectors that detect in different ways. This is the detection of the Higgs boson, for example. This is a different detection. All these different things, the beam is here, and all these different things are different detections in 3 dimensions.
Like the one behind you.
Like the one here. So they have so many different representations of this, and then of course there are numbers that, in here they have all these wires that go through here, and then all these little instruments, and they're all different detectors, just gazillions of different things that they detect with. It's just incredible what they're doing here. So, and they're able to determine a lot of things that we didn't know. Even just in the few years they've been running it, they've been able to learn a lot of new things. So it's really quite exciting. Quite exciting. And we will learn about that stuff next time. I did say we're not going to have any homework this chapter, so I'll not give any homework. But next chapter, we'll do some homework, and that will probably be our last homework of the semester, because the last chapter is Frontiers of Physics, which we're not going to do anything with, I don't think. All right.
Was there homework for chapter 31?
Well, it's chapter 31. Yeah. Didn't you do your homework? Scott? It's an easy one.
I didn't even.
Yeah, there's homework for chapter 31.
Can't even see 31, 30, 31 anymore. It doesn't show up.
No, there's no homework in that. What are you talking about? I thought there was, but apparently there isn't. I'll put some homework in chapter 31.
Oh, you don't have to. Don't do that. That's fine. We'll forgive you this once.
I need to do one more question in 30. I could not open up my own book. Open it up.
Chapter 30?
Yeah.
Okay. Oh, this is terrible. I hate when this happens.
I need to open it right now. 10 minutes, probably. I don't know. Everyone if I can figure it out or not. No, I cannot get awake this morning.
All right. Well, we'll end this recording and call it good.